Hi everyone, this is Professor Fernandez, and in this video we are going to start Lesson 8. We'll talk about Module 1 in this video, so I will get started in a minute. Let me just show you very quickly the multivariable calculus application / motivation at the start of this lesson. This has to do with population genetics, so there's a lot of good stuff here, and really the motivation is that using some of the concepts that are described in here, in one of the practice problems, you will determine an interesting upper bound on the proportion of individuals with certain blood types. So that is pretty cool if you ask me. So again, that is going to be in one of the practice problems, and it will make use of the optimization theory we develop in this lesson. So in this first module, we are going to talk about local and absolute extrema. Actually, in this first module, we'll only talk about local extrema. And then absolute extrema is module 2, and module 3 is applied optimization problems. Great, so let's go ahead and get started. This is an addendum to a nice, motivation up in the first page of population genetics. Again, I encourage you to read through that application. It's pretty cool. So the first place I want to get started is with just reminding you of what the situation was for single variable calculus when we talked about local extrema. Just very quickly, this phrase should bring up memories of maybe local maxima or local minima of a function and how we calculated that. Often we use the derivative, and we use a bunch of tests. First derivative test where you found a point where the derivative was 0, and then you checked points to the left and to the right of it, and maybe you got the sign SIGN diagrams. You found, a critical point, and then you found that the derivative went from increasing to decreasing, and that told you local maximum. Or perhaps you found that the derivative went from decreasing to increasing, and that gave you a local minimum. Or maybe you did the second derivative test. You found that the second derivative at the point was negative, and that gave you the concave down results, which suggested a local maximum. And then in the other case, you found the second derivative to be positive, gave you the concave up result to suggest that the point you were looking at was a local minimum. So again, very quick review of what happened in Calculus 1. In this lesson, we are going to generalize these insights to the multivariable context. And you'll see that the changes are not so great. We are going to talk about a second derivative test, just like we did in single variable calculus. And we are also going to talk about critical points and then calculating those using derivatives. So I want to switch to the technology first here because I want to show you what a multivariable local maximum looks like and a multivariable local minimum. So here I have graphed a function for you, and I just want to relate the terminology to, again, our view of thinking about these z equals f of xy surfaces as a mountain and walking around. So I've graphed here a function, and you can see that it has, we've seen this function before in the videos in this class. It has 2 peaks here and 2 valleys. So without having to define local maximum, local minimum, it seems pretty clear that this function has a local maximum here at this point xyz, and a local maximum also here xyz, and it has a local minimum down here at this point, and then also, if I pan around, down there, which is this point down there. So, if we are going to port over, generalize the notion of local extrema from single variable calculus to multivariable calculus, that is a first stop. A first stop in doing that is defining what we're talking about. So, based on the graph that I just showed you, you should have some rough intuition for what this definition says. So let's talk about it. So that says, consider a function of 2 variables. We will say that f has a local maximum at a point if this condition, when this condition. So let's talk about the first condition. If f of xy is less than or equal to f of ab. So what is that telling us? That's telling us, well, we're thinking of the point a comma b. We're defining what it means for it to be a local maximum. So again, think about this from single variable calculus. And f of ab is the value of the function at the point AB. So if I go now to the 3 space that we work in this course, and think just like of a hemisphere here, right? The point AB might be right there. So this is the z-value f of AB. And then this condition says that the other z-values, f of x comma y, where the input is near AB, are less than or equal to. So they are either smaller than or the same. So that's the picture here. So you're thinking here, basically if I draw a tiny little disk around AB in the xy plane, and I look at all of the values that I get from that tiny disk, right? That's all these z-values, and maybe on the other side too. You can see that all those z-values are smaller than this z-value up here. So again, we think of extending our analogy from single variable calculus, where we thought of this as humps for the local maxima. We are thinking in 3D now of local maxima as hills. So to go back to our image here, that makes a lot of sense. Thinking of this as a local maximum is thinking of it as a little hill that you climb, and same thing over here. And then the other part of this definition is the other side of that coin. So if I am looking then at a local minimum at a point, we are going to take that to mean, define that to mean that the y values when you're near that point AB are bigger than or equal to f of AB. So I actually wish that the iPad could do this. I'm not sure if it can. I've tried but failed. If I could take this picture and basically rotate it so that it would be the same picture, but it would look like this, then this bottom point here would be a local minimum, because all of the y value, all of the z values nearby, where now I'm thinking of AB here, and I'm thinking about a little disk around it, and these are the z values that results, right? All these z values are bigger than this z value here. So in this case, it should be strictly greater. Okay, so this is what we define as being local maximum and local minimum. The actual value, last part of the definition, f of AB is called the local maximum value or the local minimum value, respectively. Great. So next thing that we want to generalize that we know from single variable calculus is the notion of a critical point. We found these to be extremely helpful in single variable calculus to help us actually find local and eventually absolute extrema of a function. So here is the quite natural generalization. Suppose that I have a function of 2 variables. We will call the point AB a critical point of the function if this. So you should be familiar with these two conditions from single variable calculus. So what are they? Basically, from single variable calculus, a x value was a critical point or critical number. Sometimes a distinction is made if the derivative was 0 or undefined. That's what's happening here. So we're saying we can, since f is a function of 2 variables, we can find 2 types of, fundamental derivatives, f sub x or f sub y. So part of being a critical point is that at a comma b, both of these derivatives are 0. It's not going to do if just one of these is 0 and not the other. So we're going to require both of them to be 0 at the same point a comma b. Or, so just like in single variable calculus, sometimes you get a local max at a point where the derivative is undefined. Maybe the function has a kink or a cusp in the graph. Similarly here, and at those points the derivative is undefined. Similarly here, there's an or the x derivative at AB or the partial in the direction of y at AB, or both, are undefined. Okay, so there's an or. So if any of these two conditions are satisfied, then we call the point a critical point. Some extra terminology you might hear me use, you might also see used in other settings, is in the first case, right? Because there is an or in this definition, we kind of want to name each case, make it easier to refer back to. In the first case, we also might call the point a comma b a stationary point. Stationary comes from the idea that fx and fy are both 0 there. So there's some sense in which the function's y values are not changing, at least in these two directions. So that's stationary in that sense. In the second case, where fx or fy or both are undefined at a comma b, we may refer to that as a singular point. So that's notation that should conjure up some, cusp or kink or some, non-smooth nature in the graph. Great. So where do we head from here? So now we've generalized our notion of local maximum, local minimum, and our notion of critical point to the multivariable context. You can see down here where we're kind of heading. Remember, from single variable calculus, there was this theorem called Friedmans theorem, which basically told you that if you're looking at a function that has a local extremum, local max, local min, then the point has to be a critical point. And then, we're assuming here that we can differentiate the function. So basically, that explains all of the graphs that I drew initially. These are mostly the basic intuitive graphs that we draw in single variable calculus to think about local max and local min. And it leads us eventually to looking for places where the derivative is zero as places where we might want to examine, search for local maxima and local minima. So Friedmans theorem also translates over into the multivariable context and says much the same thing. So suppose f has a local extremum at a point, then AB is a critical point of f. So going back to the definition, what does that tell me? Either the x and y derivatives are zero there, or one or both are undefined. So again, this zeroes in, it narrows our focus. If your goal is to find local extrema, it narrows our focus to the points where the derivatives are zero or undefined. Because we know that if you have a local extremum, then you're a critical point. This is the source of a lot of confusion in single variable calculus, because often we think that it goes the other way as well. We think that, oh, if you're a critical point, then you have a local extremum there, but that's not true. And the example in single variable calculus that's always used to illustrate this, very simple example, is x cubed. If I take the derivative of this function, I get 3x squared. I set it equal to 0, solve for x, I get x equals 0. So at x equals 0, the function has a critical point. Its derivative is 0. However, as you can see here, it is neither a local maximum nor a local minimum. So again, just because you have a critical point somewhere does not mean you have a local extremum there. However, the converse of that, if you have a local extremum, then you are at a critical point. That is true. That is Friedmans theorem. So even though it doesn't work the other way, which is what ideally we would want, nonetheless, it tells us that at local extrema, you're at a critical point. So again, as I said earlier, it suggests to us that we narrow down our focus for finding local extrema to finding critical points. But then we have to do something once we've found those critical points to actually figure out if they're local extrema or not. That's why at the very beginning of this lesson, I reminded you of all these tests. First derivative tests, second derivative tests, etc. So I say a lot of that here. So the tests, as I mentioned earlier, that we use in single variable calculus, the two main ones are first derivative test and the second derivative test. I'm only going to talk here about the second derivative test. This is essentially what we do in multivariable calculus. There is no, as far as I'm aware, easier analog than this that corresponds to the first derivative test. That is, this second derivative test, as you'll see in a minute, is fairly easy to apply and gives us exactly the conclusions that we want to make. You might remember in the first derivative test from single variable calculus, even if we were able to figure out that C was a critical point, to test that, to investigate whether it's a local maximum or minimum, we needed to find points close to C and then substitute them into the derivative and then look at the sign, SIGN. And then from the sign changes, we could determine whether it's local maximum or local minimum. You can see why in the multivariable context it might get a little tricky to do this. Because if I'm looking at a point AB, and I'm trying to look at what's happening at the surface, on the surface z equals f of xy, I can't just so easily do what I did here. I can't plug in a point to the left, just to the left of c, and just to the right of c, because now I have two directions I can move in. You know, do I plug in this point and this point, or do I plug in this one and this one and this one and this one? So it's not so clear. So this is one of the reasons why, unlike the first derivative test, the second derivative test in single variable calculus, you just plug in the c value. And if the second derivative is positive, then your function is concave up near that point. Tells you it's a local minimum. So in other words, all you need to do is evaluate and look at the actual number that pops out of the second derivative at the point. That is much easier to do and does not suffer from this issue in the multivariable context. So hence why we are exclusively going to deal with the second derivative test. Okay, so all that being said, let's take a look at what the theorem says. Suppose we have continuous second partial derivatives everywhere inside a disk with center AB. So that's almost what I've drawn over here. This is a disk with center AB, meaning a circle with including its interior point and the boundary of the circle, or the boundary. Suppose that I have then that continuity and that I can differentiate enough that I can find second derivatives near the point A comma B. Suppose also that AB is a stationary point. So there's that terminology. Remember, stationary point means that fx and fy are both 0 at A comma B. We are going to define the discriminant d at A comma B to be this expression. So what is this expression? Well, it's the product of fxx, second derivative in x, with fyy, second derivative in y, minus the square of the mixed partial, fxy. Then, so here are the four conclusions. So there's a lot of stuff coming out of this theorem. First of all, if d is positive at AB and fxx is positive, then we have our local minimum. Okay? If dxab is positive and fxx is negative, then we have our local maximum. So this should, feel fairly intuitive, at least as far as this part goes. Right? Again, thinking back to calculus 1, you got a second derivative that was positive, gave you a local minimum. You got a second derivative that was negative, gave you a local maximum, right? Second derivative negative, local maximum. Second derivative positive, local minimum. And then this is the part that ends up being a little less intuitive, but we are in the multivariable context, and this condition, the positivity or negativity of the second derivative, just ends up being not enough to guarantee the results that we're looking for. So the third possibility is that dx is the discriminant value at AB is negative. Then you don't need anything else, any other conditions about fxx or fxy or any of that. The conclusion then is that fab is not a local extremum of f. Instead, it's a saddle point of f. And I'll draw for you some examples in a minute of what a saddle point looks like. As before, as in the single variable case, if d, the discriminant, is 0, the test is inconclusive. We just cannot use this test to conclude local max or local min of the function. Okay, so saddle points. So let me talk about that and then just draw some other examples here. So first example I want to draw is what a local min would look like under this test. And I'm just going to use a hemisphere as an example. Right, so this is a nice example of a local maximum. Local maximum. Let's start there. So this is one, again, kind of like the first surface I showed at the beginning of the video. This is one example of what a local max might look like near the point AB, which in this case is the origin 0, 0 of a function. A local minimum then would look like this, but turned upside down, right? So that's an example here of a local minimum. Again, I'm thinking here of AB as the point 0, 0, and the local minimum is down here. And then a saddle. What does this look like? A really simple way to think of a saddle is think of a parabola in along, one of the planes. In this case, it's a parabola I'm trying to draw in the xz plane. And then think of, opening downward, and then think of a parabola opening the opposite direction along one of the other planes, in this case, in the yz plane. And then, you put this together, and it's a little tricky to draw, but it's kind of like what you think of as being a saddle when you draw a saddle, an actual like saddle that you would use for riding a horse, for example. So I've done a terrible job of drawing this because it is quite hard to draw. But in the example that I'm going to show you in a minute, we are going to find a saddle point. So you'll see this in 3 dimensions. Okay, so some comments here. We call in case 3, scroll up here, the case when d is negative, we call it a saddle point because, as I've tried somewhat unsuccessfully to draw here, the graph looks like the graph of a saddle that you would use to ride a horse, for example. And this was the local minimum graph. Okay, the expression for d up here is one that is a little difficult to remember. It's not too bad, but still. It may be a little easier to remember it if you remember this way of computing it. So we've talked already about determinants. Determinants showed up of matrices 2 by 2 and 3 by 3 when we talked about cross products. So here is a way to remember d as a determinant. So the first row would be derivatives, second derivatives, whose first component is fx, and then fx and and then do it again with respect to x, and then do it again with respect to y. The second row is derivatives whose, I'll zoom in here, make it easier. Derivatives whose first step of differentiation is with respect to y, and then the second time is x and then y. So this is the fx and something else row, and this is the fy and something else row, and then you take the determinant of this. Remember, with a 2 by 2 matrix, we multiply the diagonals, gives us this term, and then we multiply the off diagonals and subtract the 2. So when you multiply the off diagonals, this is technically fyx times fxy, but we are going to use the equality of mixed partials fact. Okay, so that goes back to theorem 6.1.1, and it requires the function to be smooth enough, differentiable enough, and nice enough, which it will be in all of our cases. So with that, we can then say that fyx equals fxy, and that explains the square here. So this is a way to remember the formula for the discriminant d in this theorem. Okay, so we've talked about a lot, so let's do an example. And this is the first example that we will do. It's actually the only one in this video because we will keep coming back to other examples in the video and illustrating these concepts in those examples as well. So the first thing is find the critical points of the function. So I'm going to start with my f of xy here, and I will just differentiate it with respect to x. So that gives me 4x cubed minus 4y. And then I'm going to differentiate with respect to y. I get 4y cubed minus 4x. And then remember, to find the critical points, I ask myself 2 questions. Where are the partial derivatives 0, stationary points? And where are they undefined? Okay. That's going to really vary by the function. These are multivariable polynomials. They are continuous, as we said in previous videos, for all xy. They are always defined. They are never undefined. So there are no singular points in this example. There may be some stationary points. I don't know. I will have to set each of these to 0. And then now I have a system of equations. So the first one I get is x squared minus y equals 0. And then I get x cubed minus y equals 0. I get y cubed minus x equals 0. Again, depending on the example exercise you're looking at, there may or may not be a fast way to solve this. And there's no right or wrong way either. Right, your goal now is to find x comma y that solves both these equations. In this particular example, if I solve here for y, I get y equals x cubed. I can insert that over here, and I pop out with x to the third cubed minus x equals 0. So I get x to the ninth minus x equals 0. Great. And then I'm going to do lots and lots of factoring. So I factor out an x. Leaves me with x to the eighth minus 1 equals 0. It may take some time to get comfortable with all of these operations. That's where practice comes in. Because here, for example, this is a difference of squares. X to the fourth minus 1, x to the fourth plus 1. And you can always check your work, right? If I multiply this out, I get x to the eighth plus x to the fourth minus x to the fourth, so they cancel, minus 1, which gets us here. Great. So, and then you can just keep going. This is the problem that just gives more difference of squares, right? Here's another difference of squares. This is x squared minus 1, x squared plus 1. Great. And then now we have another difference of squares. And I promise this is the last one. So x minus 1, x plus 1, and then everything else. Great. And now this is all being multiplied to get 0. This term is never less than 1 because x to the fourth is non-negative. Same deal with this one. X squared is non-negative. And then so the only terms that could possibly be 0 are x equals 0. And then from here we get x equals 1. And then from here we get x equals negative 1. So I found my x values. Great. I'm making progress. I'm going to go back here. You can use any one of these equations to find y. I had already put y here as equal to x cubed. So I'm going to use y equals x cubed, and that is going to pop out my y values. So when x is 0, y is 0. When x is 1, y is 1. And then when x is negative 1, y is negative 1. And then from this, I can assemble the 3 critical points that are that we found so far. So 0, 0, there we go. And then 1, 1, right? And then negative 1 is my last one. Okay, so we have answered successfully the first one. Check. Number 2, let's classify these points using the second derivative test. Okay, to do that, we have to calculate, I'm going to scroll up here, all of the partials involved in this discriminant. So let me just mention that, we are using a theorem. So we just, by way of ensuring that we don't blindly use it, we just want to check the hypotheses. Our function f is a multivariable polynomial, so it's continuous. And the second, however many derivatives you want to take are also multivariable polynomials. They're also continuous everywhere, not just in the 3 specific critical points we have found. So all of the critical points we found are stationary points, not singular points. So all the hypotheses are satisfied. Now we're going to find the discriminant. So I need to calculate fxx, fyy, and multiply them. Subtract fxy squared. So I need 3 second derivatives that I want to calculate here. fxx, fyy, and then fxy. Going back to the function, we already calculated fx. Now I'm going to calculate another derivative of this time with respect to x. So that gives me down the 12x squared. So this is 12x squared. Going down now to fyy, here's fy, calculate the derivative of this with respect to y, gives me a 12y squared. Nice little symmetry there. And then fxy, I'm going to go back here, differentiate with respect to y. That's the only term that I see there, and I get a minus 4. Great, so now I'm going to write out my discriminant. It is the product of fxx with fyy minus fxy squared. So I get 144x squared y squared minus 16. So that's dxy. Awesome. So then I can now evaluate the discriminant at the 3 points that I got, the 3 critical points. The first one was 0, 0. So if x is 0, y is 0, all of that is gone, and I just get negative 16. So I'm just going to keep evaluating while I'm here, and then we'll go back and interpret things. Okay, so at 1, 1, I just get 144 minus 16. That is 128. And then at negative 1, because I'm squaring x and y, I get the exact same output, 128. Okay, so now interpret things. So negative 16 less than 0. 128 bigger than 0, bigger than 0. All right, and then I go back, scroll up to my theorem. One of these ended up being negative, so already I can make a conclusion. If t is negative, the y value is not, a z value is not a local extremum, it is a saddle point. So I'm going to scroll down here, and I'm going to say this implies, this implies 0, 0 is a saddle point. And again, I'll show you what that looks like on the 3D applet in a much nicer way than I could with my bad drawing up here. Okay, next one is we have gotten two other discriminant values, and they are both positive. So, positive. So I am here. The problem is that I need to check now the fxx values, because depending on whether they're positive or negative, that will classify as local max or min. So I'm going to go back down here, and for these I'm then going to check for this one fxx at 1, 1. So I'm going to go back up here. If I substitute x equals 1, I get 12, so that is positive. And then over here, if I substitute in x equals negative 1 up here, I also get 12, which is also positive. So I now know that d is positive and fxx is positive. Let's see what our second derivative test tells me. D is positive and fxx is positive. So we are, in this case, positive. Oops. Use the highlighter. Positive and positive. So f of ab is a local minimum of f. Okay, great. And let me actually go back here and put in the z value so we know where this is ending up. So we got two local minimums and a saddle point. So this was 0, 0, and then if I substitute x and y both being 0, I'm left with 1. So 0, 0, 1. And then over here, these are both local minima. And then if I look at 1, 1, and I substitute back in here, for x equals 1, y equals 1, I get 1 plus 1 is 2. Plus 1 is 3, minus 4 is negative 1. And then over here, I get negative 1 coming from this. And then I substitute in those x and y values. I again get 1 plus 1 plus 1. That is 3. And then because these are a product of two negative numbers, they're positive. So again, we get 3 minus 4, negative 1. Okay, so those are my conclusions. 0, 0, 1 is a saddle point, and these 2 points are local minima. So what does this function look like? Well, again, I'm going to try and fail, but I will try nonetheless to give you some sense of what this is going to look like before we draw it. You might say, Professor Fernandez, why would you do that? Why not just go right now and keep this video short? And I would say, yes, but I want you to be able to draw this out, or at least sketch it by hand, without needing to rely on the technology. So let's look at this point first. 0, 0, 1 is up here, and then 1, 1, negative 1. So x equals 1, y equals 1, and z equals negative 1 is somewhere down here. And then negative 1, negative 1, negative 1. So that's back here, and then over there. Okay? And these two are local minima. So again, think of local minima as, there's kind of like a bowl over there for the graph, a bowl there. Okay, and then this one's a saddle point. This is the really tough one to draw. But if you can kind of see what's going on, this bowl's going to have to come up, and this bowl's going to have to come up too. So my guess is that we have that parabola that I talked about over here, and then in some other direction, there's going to be a parabola that goes up. Okay, and then that makes this a saddle point. That is as much as I will attempt to draw, which is admittedly a fairly horrible rendition of what this function looks like. But now I'm going to switch over to the technology to show you. So let's do that. And I'm going to turn off the function that we talked about earlier. and turn on the function that we are working with now. So there it is up there. And notice that this is, not pretty bad. I did a fairly good job of predicting what this was going to look like. So there, down there, is one of our local minima, and then back there is another one of our local minima. And then I'll show you when I turn off the wireframe this saddle point right here. There's, all sorts of ways to understand the surface. To me, it kind of looks like a tooth. I don't know, so what does that say about me? Maybe I have to go to the dentist if I'm thinking about teeth. But let me show you then the saddle points. So I'm going to put wireframe only, and that at least helps us to peer in here. So if I look at the function from this angle, you can see very clearly this almost like parabolic, opening down parabola. And just to make sure, this is the point 0, 0, 1. You see the 1 there for z. So now I'm going to try to look at it from a different point of view. And you see from this point of view, you can see this, oops, where did I go? Sorry. There, that's where I was. From this point of view, you can see the parabola going upward this way. And that's a classic saddle point. Again, you think of a saddle that you use to ride a horse. You look at it from one direction, it's kind of this opening up parabola. You look at it from another direction, it's kind of this opening down parabola. And this is really the best way to do this. I mean, if I try to go into the surface, it gets, not so easy to interpret what's going on. Even if I add back some of these fancy graphics, you can see that, maybe possibly right there, at least from that view, you can see this parabola here going up, and then if you're standing there, you can also, if you move in a certain direction, you kind of fall off the graph that way, or fall off the graph this way. And of course, that would lead you eventually to one of these local minima down here. Okay, great. So that is it for this example, and I'll just go back and mention a few very quick things. So important things to keep in mind from this module in this lesson. We generalized what local maxima and local minimum were for the multivariable context. That wasn't really anything new. Neither was the critical point stuff. Basic story as usual, set the derivatives equal to 0, or where the derivatives are undefined. That gives you critical points. And how we find them doesn't change much. We look at how we find local extrema, we look at the critical points, and then we use some test to investigate them. What has changed is that because of the complexity introduced by what we talked about in this picture, basically the fact that, I can't, like in the single variable case, there's no notion of left or right. I'm in 2 dimensions. So I could move around in all sorts of different directions. The first derivative test is not something that we usually go to as a method to help us figure out or determine local maximum or local minimum of a critical point. Instead, we rely more on the second derivative test, which is a bit more straightforward, in the sense that if you calculate the discriminant and you are keeping track of the right signs SIGN, then you have nice conclusions. Unless, of course, you get t equals 0, which, parallels what happened in the single variable case. And then finally, there is a nice determinant version of the discriminant in this test that might make it easier to remember. Great. So in the next video, we will talk about absolute extrema, and we will see how, again, much of the stuff that we learned in the single variable context will generalize to this multivariable case.